Good morning to all. Yeah. Uh, so we will start today class. So we are talking about memory organization here. So in last class we started talking about that is organization of one memory module using another memory module. Okay. So let me write that question here. Like make a memory module using 512 K, I think. Yeah. Okay. So, here what we have to do? We have to make the module which has the word length 32 bit, but given memory is 8. So, what we can do? We can put 4 such memory module, that is 5, 1, 2 into 8, and then if we put in a row and if you select the particular row, each row consists of 4 such memory module, then we will get 32 bit words. Okay. So, therefore, what we have to do is say this is 512 K into 8. Okay. Similarly, okay. So, now we got the word length from here, we will get from D0 to D7, from here also it will have the 8. Okay. 512 K, this is also 512 K into 8, this is also 512 K into 8. Okay. So, here we will get it D8 to D15, this is will get D16 to D23, here we will get D24 to D31. So, you will get the total word length is 32 bits. Okay. So, now what we have to do, that address line should be how many? 2 to the power m, 2 into 2 to the power 20. Okay. That means 2 to the power 21. This should be the number of address line. But if you carefully see, this given memory module has how many address line? So, it has 2 to the power 9 into 2 to the power 10. So, 2 to the power 19 address line. So, therefore, to make this one 2 to the power 19 address to 2 to the power 21, then what you have to do? You have to make 4 rows. Okay. Similarly, so what we can do it here, here. Okay. So, each one is 2 5 on 2 K into 8. So, that means each has 19 address line. So, therefore, so if we consider this is the entire memory system, okay. So, this should have how many address line? It will start from A0 to A20, okay, total 21 address line. So, out of that, so A0 to A18, this one should be connected with the each and every memory module of size 512 K into 8. Okay. So, therefore, what we can do it simplest form here, say we can do something like that, it should be 4. So, now now what you have to do, this address line from A0 to A18, 19 address line should be connected with the address line of the individual memory module. Okay. So, therefore, so anyway you can connect. So, you have from here you have to form this memory module, yeah, no. So, this is you have to form the memory module of what? 2m into 32 using 512 K into 8. So, now let us say what you can do it, you can connect here, say you can connect here, you can connect, similarly you can connect here. Okay. Now from address line from A19 to A20 you send into a 2 to 4 decoder. So each decoder will select, say each decoder, this is a row line. So this may be connected with this one, this will be connected, please follow here. Next, this is next here. So now this you connect here. Okay. Essentially what you are doing. So first A0 to A18 19 address line you are directly connecting with memory module of 512K into 8 because it has also 19 address line. But this memory module, which one we need to make the memory system, it should have the 2M, that is 21 address line. So 19 is coming directly from the memory module that is given, and rest 2 we are passing through a decoder, and decoder is nothing but 2 to 4 decoder, and then decoders each in output will be connected with the each row. Okay. So, and then as I shown earlier also you will get the 32 bit output. Okay. Similarly, you can form also a memory module of, say, organize a memory. Okay, organize a memory unit of 2M into 8, okay, from a chip or memory unit of 4K into 4K. That means you have a which has 4096 into 40. So you can say 4096 into 4096. So this is 4 into 1024 into 4 into 1024. Okay. So therefore what we can do it here, 2 to the power 2 into 2 to the power 10, this is also 2 to the power 2 into 2 to the power 10. So in total it is coming 2 to the power 24 bits. So total memory module has those many number of bit. Okay. So 2 to the power 24 bits. So what you have to do, you have to form a memory module like that. So each row has 4096 bits. What we can do it, we combine by 8 flip-flop. So then we will get the data line of 8. So therefore 4096, that means 2 to the power what, 4 into 1024. So this is 2 to the power 2 into 2 to the power 10. So 2 to the power 12. So now what we will do it, 2 to the power 12 we combine with bit 8. So 2 to the power 3. So 2 to the power 9. So we can group each row, each group consists of 8 flip-flop. So therefore what we can write it here, so we have a memory module of 4096 into what, 512 into 8, 2 to the power 9 equal to 512. And this memory unit, how many address line it must be? It must be 21 address line. Okay. So therefore what we can think of, we have a memory module of 4096 into 512 into 8. Okay. So total number of address line is 21 for this memory module. From this memory module we have to make of 2M into 8. Okay. So to solve this issue, what we can do it, we have the address line from, you can write A0 to A20. So first we will select the each row. How many row this module has? 4096, that means 12, right? So 4096 is 2 to the power 12. So A0 to, okay, sorry, A0 to A11, then A20. Okay. So A0 to A11 we pass to a decoder. So decoder is 4 to 2 to the power 12 to 2 to the power 12 decoder. we can say it is choosing row, so we can say row decoder. So this will be connected to the row. Now rest A12 to A20, this will go here to another decoder. Okay, this is also decoder. So this is what, how many? So it is having 512. So it should be 9 to 512 decoder, and this decoder will come here. Okay, or maybe we can write it here. So this is what, 9 to 512 decoder, this is we can name. Okay, so what is essentially what it is doing, say we have 4096 rows, and each row consists of, say this is 1, this is 1, this is 1. So this is 8 flip flop, this is also 8 flip flop, this is also 8 flip flop. So such 512 flip flop we have. Now at a given time what we have to do, so particular based on the one address, first we will select the particular all row, one row is here, one row consists of 512 group, each group has 8 flip flop. So once you select this one, next what is the task? So out of 512 groups we have to select only one. So for that we have to have a decoder of size 9 to 512. So that decoder will select any one of the 8, any one of the flip flop. That means this decoder will select only the 8 flip flop, and that output will go here. So that will be treated as D0 to D7. Okay. So this will be the output. Next we will talk about memory mapping. So first we talk about the memory hierarchy. Okay. So in memory hierarchy we have a here processor register and L1 cache, then we have L2 cache or cache, then we have main memory, then we have secondary memory. So obviously data will be transferred in both way. Okay. So now if you go up, this will indicate that is increasing order, so speed will increase. Okay. It's not only the speed, cost per bit also will increase. However, if you go down here, the size in a system will decrease. Okay. So this is memory hierarchy. So as you know that I will tell you here. So what happened exactly, we have processor here, then we have main memory or RAM, whatever we just taught you can consider. Okay. So in between we have a special memory which is much faster than the main memory, is called cache memory. Okay. So this cache memory, what happened exactly, as you know that whenever processor wants to read some data, so processor should generate the address. Okay. What happens is, suppose processors wants to read particular word, a word from a main memory. Okay. So processor always generate the address of the main memory. Processor does not know the existence of the cache memory. Okay. So now what happened? Then address, that corresponding address consisting of that particular word is placed at MAR, memory address register. So we are considering we have a something come here MAR. So then this address will be placed to the main memory. Okay. And what happened here, then main memory will transport the data to the processor. Okay. At the same time, what will happen, that block consist of the word, the desired word is transferred to cache memory, and the word is sent to processor. That means this particular word is sent to processor and then block is sent to the, so here block. Similarly, if it wants to write it, so where to write, so it places the address here and then which one needs to be written, so that should be sent to, that particular word should be sent to the main memory. First it will write to here cache and then main memory. So, essentially, and this also will be connected here. So, processor generate the address of the main memory, it never generate the address of the cache memory. Now, once it gets the address here, then the entire memory mechanism will catch that address, and based on the mechanism it will be sent to the cache memory as well as the main memory based on the situation, and then if data is available in the cache memory, then the data will be transferred to the processor. If it is not available in the cache memory, then the, as I said earlier, that block will be transferred to the cache memory, however, the word will be transferred to the processor. Processor will not take the entire block, processor only wants, processor generate the address, it generates the address for particular word only. Okay. For make the system much faster, what we are doing, entire block we are transferring. So, what happen is, say suppose we have a main memory of address 000, 001 and so on. So, then 009, block is nothing but the continuous memory addresses are called the block. Okay. So, now what happened, processor wants the word which is located at the address 001. So, then processor will generate the address 001, processor want this one, but main memory module will send entire this block here, this entire block of the 10 word will be sent to the cache memory, and then particular word will be sent to the processor. Okay. So, now question is, why that entire block is sent when the processor needs only a particular word? Answer is, see here, because when we access the array, okay, so if we access the array of say in the ith location, very likely we want to access the, in the next phase is the I plus 1's indexed element. Okay. So, if it is 10, so very likely we want to, programmer wants to access the 11th location in the array. That means, processor wanted this time is 001, maybe next time it will ask for the word which is located at 010. Now, again it has to go to the main memory and access it, and then speed of the cache memory is much higher than the main memory. So, therefore, next time processor does not need to go to the main memory, it will get from only the cache memory. Processor will generate the address 010, once it trapped 010, it will search whether this particular address, obviously this address is associated with this word. So, then this particular address is available in the cache memory, it is not address, it is the cache, it is the content at that particular address, whether it is available or not. If it is available, it will be transferred to the processor, no need to go to the main memory. Okay. So, this is very likely that next address will be very next access refer address will be within the block. So, that is why entire block is transferred. Okay. So, another thing may happen within a loop, see same code we are using repeatedly within the loop. So, therefore, this fact that whether this next address will be within the block in nearby block, or this the same word might be used next. Okay. So, these are the things it generally happens, these are the things are called the locality of reference here, locality of reference. Okay. So, locality of reference, it can be temporal locality or it can be spatial locality. See, spatial locality is based on the space, temporal locality based on the time. Okay. So, this is something, it is based on this heuristic, like recent past is the good indicator of near future. Okay. So, this can happen in two scenario. One is the spatial locality, say let us say here in Raurkela, here right now we have the weather in campus is weather is cloudy. So, very likely that nearby place a railway station also will have the same kind of weather, that is cloudy weather. Okay. So, this is something called example of the spatial locality. Okay. And what is the example of temporal locality? Spatial locality is accessing the memory index or say uh, elements of the array. So, one by one we are accessing, that is example of the spatial locality. Another example is the temporal locality. Say temporal locality is based on the time. So, now we can say now time is 8:30. So, weather at campus is cloudy. So, we can expect that. So, after 15 minutes or 20 minutes weather in campus will remain cloudy. So, this is the example of the temporal locality. Okay. So, temporal locality is based on the time. So, very likely the same thing will happen after few minutes later or after say 10 minutes later and so on. So, that is something called temporal. So, on the other hand, spatial locality is based on the space. Temporal locality, an example in a coding is like same set of code we will be using or same set of data we will be using next. Say within a loop, very likely we are using same type of instruction, say let us say for 10 or 20 times. So, this is the example of the temporal locality. Okay. So, now how do you do it? Maybe as I said earlier also, probably that is the size of the cache memory is much lesser than the size of the main memory. Okay. So, based on that we need to have a different mapping scheme. Okay. So, that mapping scheme is something we will come here, but before that I will tell you how the operation happen in case of the cache memory, when we have the cache memory. Okay. So, here say, so particular flow chart, if you want to see it, you need to see the book stallings. Okay. So, if we start from here, so what is the first task? It receives the address array from the CPU, receive address array from processor. Okay. Now, question is, as I said, the CPU generated the address, a particular address. Okay. So, now we need to check, is the block containing the array is in the cache, is the block containing in array in cache. If it is yes, then fetch the array word and deliver to CPU. Okay. So, this is end. So, if it is no, that means that particular word is not there in the cache memory. Then what we have to do? So, access main memory, access for access main memory for the block containing array. Okay. Now, you have to allocate the space, allocate cache memory, allocate cache slot from for the block, main memory block. Okay. So, once it is allocated, then as I said that word will be transferred to the, so deliver array word to processor and block to the cache. This should go parallelly. Okay. This part I already said, right. So, first processor will generate the address and then memory module will check whether that particular block which consists that particular address is there in the cache memory. If it is not, then that main memory blocks will be transferred to the cache memory and that word will be delivered to the processor. So, here this part, now we will focus on this one, that is allocate the cache slot. Okay. What we studied here, size of the main memory is much larger than the size of the cache memory. Okay. And what we see ki size of the cache memory is much smaller than the main memory, and we are expecting that word referred by the cache memory referred by the processor must be available in the cache memory, even though size is also much smaller than the main memory. Why this happen? Because of the locality of reference, as I said earlier. Okay. So, it is found that if you keep the size of the cache memory of same of that of the main memory, your performance will not be very much improved if you keep the size of the cache memory is much smaller than the main memory. So, as you understand that cost of the cache memory is much higher than the main memory. So, therefore, generally we keep that system designer keep generally the size is smaller and it achieve very close to the performance of the system if we keep the size of the cache memory is the same as the main memory. Okay. So, now what we will say, basically what I said here ki size of the cache memory is much smaller than the size of the main memory. So, we have a cache memory here, we have a main memory here, and what we understand more here. So, this is main memory, this is cache memory. What we understand more here ki each main memory whenever transfer the data, it transfer in a block. What is block? Block is nothing but the fixed size. So, if you divide the main memory into a number of what is called partition. Okay. So, that let us say we have a partition here, we partition here, we partition here, here. So, that each partition is called the block. So, block is nothing but is a partition in main memory. It is a fixed partition, that means size of the partition is remain fixed for any one of the any block. Okay. So, let us say size means, so one example, let us say I have a memory, main memory, so of 1000 bytes, that means it can store 1000 bytes. So, address it can start from 000 to 999. Now, what you do it? You divide the main memory into a number of partition. So, and then each partition will have only 10 bytes. So, 0000 to 009. So, this will be one block. So, this is we are saying block, this is partition 1. Similarly, we will have another block and so we will have another block. So, how many block we will get? So, we will get 100 blocks, right. So, last block will be 99. So, this is block 0 to 99. Similarly, cache memory is also divided into blocks and then the size of the block, size of the block in main memory is same as the size of the block in cache memory. So, this is also called block, this is also called block. To remove this one, what we can say? We can say size of cache line in cache memory, then no need to say ki cache. So, what we understand ki block size in main memory and cache memory remain same, but obviously total size in the cache memory is less. So, therefore, number of blocks in cache memory will be obviously lesser than the number of blocks in the main memory. Let us say this is, it can accommodate only 100 words. So, therefore, how many blocks it will have? It will have only 10 blocks. So, then number of cache line in this example is 10. So, number of blocks in main memory is 100. Okay. So, now in the flow chart here I said ki before transferring the data, so allocate the cache slot. That means essentially it is saying, as we understand ki there is no one to one corresponding from the main memory to cache memory, because size of the cache memory is much smaller than the main memory. So, therefore, when we want to transfer a particular block, let us say 65 block. So, we should know where it should be transferred into the cache memory, because we know that this entire block will be fitted any one of the block in the cache or any cache line, but we have to have a mechanism that this block will go any one of the in the cache line. So, that scheme is called the mapping scheme. Okay. So, that which block of main memory will be placed in which cache line, that is called the mapping. So, basically whenever the particular block needs to be transferred to the cache memory, first task is it should allocate the space or it should allocate the cache line for that particular block. So, the allocation of the cache line can be done mainly in 3 ways. Okay. So, that is something called mapping. Okay. So, therefore, next topic will be main memory to cache memory mapping. So, we can say main memory to cache memory mapping. Okay. So, this essentially it is allocating the cache line. So, this is nothing but allocation of cache line for a main memory block. So, there are 3 major scheme. One is called direct mapping, then is called associative mapping, another is called set associative mapping. Okay. In case of the direct mapping, okay, we will complete this class with one example in case of the direct mapping. So, we are talking on direct mapping. So, in the last example we have the cache memory of 10 blocks. Okay. So, we have 10 cache line, then we have main memory of 99, not 99, 100, what 100 blocks. Now, CPU generate the address of main memory. So, main memory address it start from 00 to 999. So, let us say CPU generate the address, let us say 765. That means, in a particular location 765, this particular word CPU wants, and we divided the block here starting from 0 block and so on. So, total 99 blocks we have. Therefore, 765 this address also will be in a particular block. So, what will be the block number? So, block number for this particular word will be what? 76. Okay. So, now in case of the direct mapping, so okay, direct mapping how will allocate? So, allocated cache line will be I, that is equal to j modulo m, where j is the block number of main memory, m is the number of cache line, and I is the cache line. So, therefore, we have 765. Okay. 765 what is the block number? Block number is j is 76. Now, you do 76 modulo 10. So, 6, right. So, therefore, cache line will be 6. So, this particular block in the cache or cache line will be allocated for this block 76. Okay. So, this will be elaborated in next class. What is the advantage of storing in the block instead of individual? Because when we are transferring data from main memory to cache memory, we are transferring in a block. Why we are transferring in a block, that is your question, right? Because next time whenever processor wants to get the access of the word, very likely it will access the next word or maybe the same word. So, whenever we are using special references, okay, locality of references, that is very likely that processor will ask the next word in the particular block, because within a block the all addresses are consecutive. That is why we put in a block and then block is transferred from the main memory to the cache memory. With that, I conclude today's class.